This second session will be about linear models. So the first session was about the sample size. The second one is about how to recognize what are the different components of the variability of our observations, and the composition of the variability will help us to better decide whether our treatments are significantly different from doing nothing, or from the reference treatment or whatever. Okay, so this is called, the second part is called experimental design, and we will see just a few ideas about it. So let's start with the most simple one, that is called the completely randomized design. So let's say that we are testing a new drug for blood pressure, and we want to compare it to a placebo, and we will use 1,000 people. Don't care about the numbers, so it is just to make it very easy. And for one of the groups we will give a placebo, the other group will receive our drug at a given dose, and we will randomly assign the people to each one of the groups, and we will have for instance, what is the systolic blood pressure for each one of the people. And we have here this notation where we have two subindexes. The first one is the group where you are, and the second one is the person within that group. So we would have group 1, person 1, group 1, person 2, group 1, person 500, and the same for the second group. And then we can compute the overall the mean of each one of the groups, so the mean of all the people receiving the placebo and the mean of all the people receiving the treatment. So we don't care about the specific person, so we have average over the persons, and then what we have is an average of the group. So we would have the observation for group 1, and since we don't care about the person, we will use a dot. And so we have the mean of 1 dot, the mean of 2 dot, meaning that we don't care about the people. And if we don't care about the people and the groups, we will have the overall mean, that is averaging over all the 1,000 people. So we will have y dot dot. Okay, so the next step will be to assume what is the data generation model. So how have we reached to get these observations? And these observations, linear models, they get your observations by adding terms, and the terms that are added is an overall mean plus something that depends on the treatment that you have received, plus something that depends on the person, the specific person. And there is a constraint in all these linear models, that is that the sum of the treatments have to be 0, and we will see it in more detail in the next slide. The problem is that this decomposition is not unique. So as humans, we tend to think in this way. So let's say that all our 1,000 people, they all have a high blood pressure. So they are all patients with high blood pressure. So in the control group, we would have the observations in the control group would be the mean of all those high blood pressure people, and then because you are in the placebo, there is no effect of the treatment, so we would have that overall mean plus overall mean of the high blood pressure people, and plus 0 plus something that depends on the person. And then in the treatment you get a decrease by 2 units of that systolic blood pressure. But we could explain the data in this way, but we could also explain it in this way. So now the mean that we will use is not the one of the high blood pressure people, but we can use the mean of the overall people that we have observed, so the ones in the control and the ones in the treatment. So now this overall mean is a little bit smaller, and then you get +1 if you go to the placebo treatment, or -1 if you go to the drug. And this shouldn't be misunderstood. So for instance, this doesn't mean that there is an overall blood pressure and then if you go to the placebo your blood pressure increases. That doesn't make sense. What makes sense is that the difference between the control and the treatment group is 2, and it is 2 here in this model, in this decomposition. It is also 2 in this decomposition. And the advantage of having this constraint, sorry, here, and the advantage of having this constraint that the addition of the treatments is 0, so +1 -1 is 0, it has two advantages. One is that it makes the decomposition unique, and the second one is that we will save 1 degree of freedom that we will learn a little bit later what it is. Okay, so we have this decomposition. We have to estimate the different terms, so we have to come out with an estimate of what is mu and what is the effect of the treatment. And a natural way would be, okay, so the overall mean, an estimate, that is the hat. So an estimate of the overall mean is simply the mean of all the individuals. That should be more or less equal to this underlying population mean. And population understanding, population of control plus treatment groups mean. And the same for the treatment. So an estimate of what is the effect of the treatment could be what is the difference between the mean of the group receiving that treatment and the overall mean. That is what you have here. So yeah, these very simple rules to calculate, they come after a number of simplifications. One of them requires that the number of individuals in each one of the groups is the same, so 500 500. But yeah, so this is called balanced experiments, and we will not get into those details, but just for you to know that these very simple rules of calculations do not always apply. Okay, so now how do we know if our treatment is effective? So for instance, let's say that we have this situation where all the people in the control group, they are significantly above the people in the treatment group. But we may be in some other experiment in which the difference is not so clear, so they seem to be a little bit lower, but given the level of noise that we have in our observations, this small difference probably it could be caused by chance. Here it is much less likely that this large difference is caused by the chance of the variability of our observations, and we have to quantify that. And for this quantification, what we will analyze is what are the distances between each one of the individuals and the two means represented here. So one is the mean of its group. So you have a person in the placebo group. What is the distance between that person and the mean of that placebo group? The other one is what is the distance between that person and the overall mean. So you may remember from your statistics courses that if you measure the distance between all observations and the overall mean, that is almost the variance. To be a variance, you have to divide by 1 divided by n minus 1, n being the 1000, the 1000 people that you have in your experiment. So we are not dividing, but this is almost a variance. So this is called the sum of squares. So this sum of squares is the distance between everyone and the overall mean, taking into account both control and treatment groups. The other one, so we can decompose this sum of squares into two components. One is related to the distance between each one of the individuals and the mean of its group. So this is a person from the placebo group. This is the mean of the placebo group, how far you are from the mean, and that is this this distance in blue. So that is the one that we have represented here, And the other one is how different the mean of your group is from the overall mean. For instance, here we see that the mean of your group is not too far from the overall mean, while here it is much farther. So we start to see where we are trying to get. So we are trying to decompose the overall variance into two components. One is explained by the treatments, this one. The other one is explained by the residuals, by the variability of our observations, by noise. And what we want to show is that the variability explained by the treatment is significant with respect to the variability that we observe in the residuals. Actually, the most famous technique used here, that is ANOVA. ANOVA is analysis of variance. And also you may remember, you may relate this to the sensitivity that we wanted to have when trying to get to specify whether, or to determine whether the 0.66 deviation that we had in our tablets in the first session was significantly different from the target value, 250 milligrams. And we had to compare this 0.66 milligrams of deviation with respect to the variance of noise. So the variance of noise there, it was 1 milligram. That was the variability of the tablets when manufactured. Okay, so here we will also compare these two sums of squares. Okay, so then let's see how to compare them. So we will have three components. So we will have the sum of squares, we will have the sum of squares of the residuals, and the sum of squares due to the treatments. And we will have something that are called degrees of freedom. So the degrees of freedom are somehow, the true concept is something geometrical. There is a very nice connection between geometry of linear spaces and statistics and ANOVA and linear models and all that. But we may think of them as coins. So whenever you do an observation, you are gaining a coin. So if you do 1,000 observations, you have gained 1,000 coins. But then you have to spend your coins, because you have to estimate parameters, and every time you estimate a parameter you have to pay a coin. So you have to estimate the overall mean, you have to estimate what is mu, so, and you have to always estimate that, and that is one coin. So for the sum of squares, somehow this is an estimate of the overall mean, so you have to spend one coin on the overall mean, so you have only left n-1 degrees of freedom. Okay, so what about the treatments? We had two treatments, so we would have to estimate two parameters. So the contribution, this Ti or Tj, we have to compute two Tjs, one for the placebo, one for the drug. But there is a trick, the sum has to be 0. So once I estimate one of them, the other one comes for free. So if I have T treatments, I only have to spend T-1 degrees of freedom. And then all the other degrees of freedom, they go for the residuals. So all these epsilons here, they also need to be estimated. So I have n, the difference between this one and this one, they go for the residual. So just to put numbers here, so if we have 1,000 people, we would have 999 degrees of freedom in total. One of them I spend it on the treatments, and the other 998 they go for the residual. Okay, so I have to compare these two terms, but it is not a fair comparison. We have used 998 parameters to estimate this one, or to calculate this sum of squares, while we have only used one parameter to account for all this variation. So somehow we have to make this comparison not at the level of sum of squares, but at the level of sum of squares per degree of freedom. That is called the mean squares. So we divide the sum of squares by the number of degrees of freedom. And you have to divide by the number of degrees of freedom for the treatments, for the residuals, and now you can compare these two. And this comparison is called an F-Snedeker comparison. So you may remember this statistic that we used in the first session for the set statistic that was following a Gaussian distribution. So now it is an F statistic, and it follows an F-Snedeker distribution with t minus 1 and n minus t degrees of freedom. So somehow the number of degrees of freedom in the numerator and denominator, they participate in the definition of the distribution. Okay, so let's put numbers. So let's say that we have in total for this blood pressure experiment, we have a total variation of 13,800. And we have collected 999 degrees of freedom. One of them goes for the treatments, which are explaining a sum of squares of 256, and the other 998, they go for the residuals that are explaining the remaining. So the add of all these two sum of squares have to be the total sum of squares, and the sum of these degrees of freedom, they have to be the total number of degrees of freedom. So how much sum of squares a single parameter of a treatment is explaining? So we have to divide these two, but it is the same because the denominator is 1. How much a single parameter, a single degree of freedom of the residuals is explaining? But they are explaining much less because the ratio between these two is 13. So the fair comparison, that is 256 compared to 13, the ratio is about 19, and this is larger than a threshold. So you may remember from the first session, we put the threshold either in the p-value or we put the threshold on the Z score. So here we are putting the threshold on the F score, if you want. Okay, so this one is much larger than this, so we reject the null hypothesis. And we have shown that our treatment to blood pressure is useful. Okay, so this is completely randomized design. What about if we have blocks? So if we have blocks, so let's say that we think that the age may make a difference in our measurements, or the fact that you have diabetes or not diabetes, it may also have a difference. And this experiment will be made in two centers, and it may be that the person measuring the blood pressure in the first center is not doesn't measure in the same way as the person in the second center. So part of the variability is caused by the person. So if you think that these are factors that affect your measurements, these factors are called blocks. And these blocks, we will have a little bit more on blocks later. But what you have to do is to make very homogeneous groups. So the people here in this at this point, they are all in center 1, they all have diabetes, and they are all younger than 55 years old. So this group is as homogeneous as it can be in terms of my variables, and there it is where I randomized. So I randomized these people to the control and to the experimental group, and the same for the other ones. And now my model for the generation of the data is like this. So you are a person. So my observation will be an overall mean plus something that depends on the block you are, and this block here we could deal it in different ways, but here I'm just showing, for instance, one block, not 3, because I don't want to make this formula too complicated. But so something that depends on the block that you are, plus something that depends on the treatment, plus something that depends on the person itself. And just to make the composition unique, again, we add these two constraints, that the sum of all the block contributions have to be 0, and the sum of all the block of all the treatment contributions have to be 0. And then the sum of squares is decomposed now in 3 terms. One is coming from the treatment, the other one from the residuals, and now there is a new line that is the one coming from the blocks. And again, we have to make we have to count how many degrees of freedom are left or are spent in each one of the lines. So because of this constraint of adding up to 0, we spend 1 degree of freedom less. And the comparison has to be done at the level of mean squares, but we are interested in the comparison between the treatments and the residuals. So that means that, for instance, let's say that we have identified that men and women, they have different blood pressures. So our block now will be sex or gender, and we have the same sum of squares, the overall sum of squares, and the treatments explain exactly the same. So if you compare these two numbers to these numbers here, they're exactly the same. So the treatments and the overall sum of squares are the same, do not change. What changes is that now the gender explains quite an amount of the sum of squares, because men and women, they have constitutively a different blood pressure. So a big part of the sum of squares is explained by gender. And then this sum of squares has been taken out from the sum of squares that I could not explain. So before, because I didn't consider gender, I was not able to explain part of the variability, and I assign it to the person. But now, because I know the gender of that person, that variability is accounted by the block, while the residuals, so whatever other variability I'm not able to explain goes still to the residuals. So the addition of these two numbers now, the blocks and the residuals, the new residuals, has to be the addition, the residuals, the sum of squares of the old residuals. But now I have been able to explain it a bit more. So it doesn't come for free. So I have to spend 1 degree of freedom here, but it is very, very cheap. So actually it is the variable that explains most of the variability. So it is the gender. And the residuals now, they have lost 1 degree of freedom that has been spent on estimating the contribution of the gender. So now I want to show that my treatments are above the level of noise. So I have to compare the mean squares of my treatments to the mean squares of the residuals. And now the ratio is not almost 19 as it was before, but it is 21. So I'm even more sure that my treatments are effective. So introducing blocks is a very, very good tool to account for possible sources of variation that otherwise you wouldn't be able to explain, and they would go into the residuals. So as you will compare your treatments to the residuals, by accounting this extra variability that can be explained by the blocks, this comparison between treatments and residuals is much more meaningful. And it may be that the blocks really explain something. It may be that the blocks do not explain anything. It is like an insurance. So the block is, if the block makes a difference, I will be able to explain that variability. If it doesn't make a difference, then the block itself would be more or less in the same situation as here. So there is no difference between the plots. Okay, so now this idea of trying to explain the variability by different components can be taken even further. So this is called factorial design. So in the factorial design, we will try to explain our measurements based on a number of factors. So let's say that you want to make the best cake in town. So you think that there are a number of factors that can affect. So how much, what is the temperature of the oven, how much sugar you add, how much flour you add, and how many eggs. And you have for each one of these factors or these variables, you have different levels. So for instance, let's say for the oven you have 3 possible temperatures, and for the sugar you have 5 different possibilities, and for the flour you have only 2, and for the eggs you have 3, let's say. So you try all combinations of all versus all, and for each one of the combinations you measure somehow what is the taste, the color, and the consistency of the mixture in your cake. And you have to put numbers, so you have to put a number on the color, you have to put a number on the taste somehow. But okay, so let's say that these are our factors. Okay, so now with this factorial design, we open a new door. We open a new possibility to see whether there could be combinations that cannot be explained by the factors alone, but by the synergy of these factors. Let's see an example. So let's say that you're interested in an educational program that you would like to see whether you want to teach statistics to a group and then or to a number of people, and then you can have 2 possibilities or 2 factors affecting the outcome. So how much statistics they learn. So one possibility is to have 1 hour per week of statistics or 4 hours per week. And the other possibility is to have these classes either in their normal classroom, or in a separate room. Maybe when they are in their room, they are more efficient in learning, or it may be the opposite. It may be that when you take them out of the standard classroom and you take them to somewhere else, they pay more attention or they are distracted. So you never know. But you think that these 2 factors, they can affect the scores that they get in statistics. So you have 2 possibilities for each one, 2 levels for each one of the factors, and you would have 4 combinations. So you could have 1 hour per week in class, 4 hours per week in class, 1 hour per week out of class, and 4 hours per week out of class. Okay, so now you come out with a model of how these 2 factors will affect your observation. So you will give an exam, you will get the grades, and so you have the grade for each person, and each one of these persons they have received a given amount of time. You have 2 levels. So this is like your treatment before, the control and the drug. So now it is 2 levels, 1 hour, 4 hours. And the second factor is the setting, so whether in class or out of class. And then something that depends on that person and that you cannot explain. So let's say that the average of all these people in these 4 combinations, they are these ones. So you have 1 hour out of class, you have the score between 0 and 10, let's say it is 5, and for all the groups they are 5. So here in orange you have the marginal mean. So the mean of all people out of class is 5, the mean of all people in class is also 5, and 4 hours is also 5, 1 hour is also 5. So now, what are our estimates of each one of the contributions? So we have the overall mean. The overall mean, very easy, it is 5. And then we have the mean of this 1 hour. 1 hour would be the 5 that we see in 1 hour minus the overall mean. So we get 0, and because also 4 hours, so the addition 1 hour plus 4 hours has to be 0. So if this is 0, this also has to be 0. And the same for in class or out of class, so the contributions are also 0. So if I want to explain any one of these cells, so for instance this combination here, I would say, okay, this mean of this group is an overall mean of 5 plus a contribution of 0 because they are studying 1 hour per week, plus a contribution of 0 because they are out of class, and that's it. And something that depends on the person, but here we have the means, not the people. Okay, now what if I get these means? So I get 5 for the people studying 1 hour, 7 for the people studying 7 hours, and 6 and 6. So I can do the same decomposition. So the overall mean is 6, and then the difference between 5 and 6 is the contribution of 1 hour, that is -1, and if this is -1, the other one has to be 1. And out of class or in class, the mean of out of class is 6, the mean of the overall all data here is also 6, so out of class or in class doesn't make a difference. Okay, so let's say that the scores are these ones. So if the scores are these ones, yeah, so let's see how to explain this mean of 5. Okay, so this mean of 5 would be the overall mean, that is 6, plus the contribution of being 1 hour per week, that is -1, so it is 6 minus 1, plus the contribution of being out of class, that would be 0, so it is 6 minus 1 plus 0, so this is 5 and it is this 5. And what about this one? So this one would be the overall mean, that is 6, plus the contribution of 4 hours, that is 1, plus the contribution of in class, that is 0. So we get 7, that is what we observe here. Okay, so let's say that the data that we get is this one, and we already know the mechanism here. So now we can compute what is the contribution of 1 hour, 4 hours, in class, out of class, and if we want to explain this 9, for instance, would be the overall mean, that is 7, plus the contribution of being 4 hours, that is 1, the contribution of being in class, that is also 1, so it would be 7 plus 1 plus 1, that is 9. Okay, good. So what if I get these numbers? If I get these numbers here, I would do the same procedure. So overall mean is 6, but then the in 1 hour, 4 hours, there is no difference, and out of class or in class, there is no difference. So all these contributions of the main factors, they are 0. And if I want to explain this 7, I cannot, because I would say, okay, it is the overall mean plus 0 because you are 1 hour in class, plus 0 because you are out of class, and then I get 6, I don't get 7. And the same here, I would get 6 and not 5. So there is something else that I'm not explaining with my model. So these two factors alone, they are called the main effects. So this is the main effect of being 1 or 4 hours. This is the main effect of being out of class or in class. But I cannot explain this data, so I have to add something else. And this something else are interactions. So the interactions between the factors means maybe 1 hour out of class is as good as 4 hours in class. For some reason, when you are out of class, you are more, you pay more attention, and then with 1 hour is enough. While if you are in your same class, then you need 4 hours to reach the same level. So these interactions that you cannot explain by the main factors alone are what are called the interactions. So you may think of this as synergies, and the synergies, so it is these two levels together, they are particularly good or they are particularly bad, and then you can compute the interactions as whatever is left until I reach the mean of the cell. So I was explaining 6 in each one of the cells, and here I need an extra 1, here I need an extra -1, an extra -1, and an extra 1. And actually the interactions, they are also constrained. If you see by rows and by columns, they all add up to 0. So 1 minus 1 is 0, 1 minus 1 is also 0, -1 plus 1 is also 0. So if you add by rows or by columns, you always get 0. So that means that once you know one of them, automatically you know all of them, because of these constraints that they have to add up to 0 by rows and by columns. So they're very cheap. These interactions are really cheap, in terms of degrees of freedom. And here it is just again a highlight that the decomposition that the factorial analysis does is not the one that we would do as humans. So if you get this data 5, 5, 5, and 7, so what you would conclude is that this so the overall mean is 5, and then this combination of 4 hours in class is particularly good. But this is not the combination that this is not the decomposition that factorial analysis is doing. So they do it, they spread this difference of 2, they spread it all over the place. So you see the overall mean is 5.5, then you get minus 0.5 here as main effect, 0.5 here. All the interactions are plus 0.5 or minus 0.5. So this difference of 2 is spread all over the place. Okay, so yeah, this is just a reminder of a little bit of the calculation. So this is our model now. So we have the main effects, we have the interactions, we have something that depends on the individuals, we have a lot of constraints that give us, save us a lot of degrees of freedom, and the different sum of squares, number of degrees of freedom, and we would expand our table to account for the new term. So we would have the total sum of squares that is decomposed into a part explained by the main effects of the first factor, the main effects of the second factor, the interactions between the two factors, and then something that I'm not able to explain that goes to the residuals. And in terms of degrees of freedom, this one is using p minus 1, this is using q minus 1. This is the product of these two, so p minus 1, q minus 1, and then all the other degrees of freedom, they go for the residuals. So let's see an example. So let's say that we want to test how a mammalian water balance hormone is affecting the water uptake in amphibia. So amphibia mammalians, they are quite different. Let's see if the hormone for water balance in mammalians, they somehow has any effect in amphibia. So I will have two species, frogs and toads. So I have a factor that is the species, and I will have another factor that is the hormone, if I give the hormone or I don't give the hormone. So I again have two levels for that factor, and it may be that the amount of water that it takes, the animal takes, depends on whether the previous hour before the experiment the animal was in water already or not. So my experiment will be, I will weigh the animal, then I will inject the hormone, and then I will put the animal in water, and after half an hour I will weigh the animal again. I will see the difference in weight. So maybe if the animal was in water already before the experiment, this difference in weight may vary. Okay, so what is my model? So a full factorial model would say, okay, so your observations will be an overall mean plus something that depends on the main effects of the three factors plus something that depends on the interactions of pairs of factors plus something that depends on the interactions of the three factors altogether. So the three factors could be there is a special synergy between frogs that have not been in water before and that receive the mammalian water balance, the mammalian hormone. So these are the third order factors. Okay, so let's say how many groups do we have? How many combinations? So we have two species, two moisture levels and two levels for the hormone. So we have 2 times 2 times 2, that is 8 possible combinations, and we will use 2 animals per treatment, so 2 animals per combination. So we have in total, we have 15 degrees of freedom, and we have to spend 1 degree of freedom for the species, another degree of freedom for the moisture, another one for the hormone, for the interactions. It is 1 times 1, 1 times 1 all the time. So we have 1 degree of freedom for each one of these interactions, and the remaining, if you count, we have 7 degrees of freedom for the main effects and the interactions, and the remaining, that are 8, they go for the error. You may remember here the resource equation that we had before, that we said, okay, for the residuals there should be something like 10 to 20 degrees of freedom. Here you have it. So we don't have 10, we have 8. So we will have a little bit, what we have chosen is what is the effect size that we will be able to detect. And we have decided it somehow implicitly. Okay, so now we compare each one of the mean squares to the mean square of the error, and we compute we don't have here the p-values or the f, but we have which ones are significantly statistically significant. So we see that the main effects are statistically significant, and the interaction between a species and hormone is significant. So, and it makes sense. So probably different species have different the hormone has different effects on each one of the species, but there is no interaction between the species and being in water before. So we see here that the sum of squares that this interaction is explaining is around 39, and the mean squares of the residuals is 34. So we see that this difference, this ratio, is almost 1, and while the ratio between the species and the mean squares is 500. So we see that the species is the one that explains the most, and then the second one is whether the animal was in water before or not, and then we have the hormone and the interaction between species and hormone, and then the rest, the ones that are not statistically significant, they are summarized into a single line: lack of fit. Okay, so now we know ANOVA. Is it better a one-way ANOVA, a two-way ANOVA, or factorial design? Factorial design and two-way ANOVA is the same. So is it better to separate into factors, or we can use the one-way ANOVA as an omnibus tool? Okay, so we could, the advantage, then the one-way, two-way, three-way ANOVA means the number, the 1, 2, 3 means the number of factors that you have. So the advantage of separating into factors is that you can attribute how much variability of each one of the factors is having. So let's see an example. So let's say that you're interested in the optimal combination of the number of meals and the daily calories for a weight loss diet. And you think of two levels for the number of meals, so you have 3 or 5 meals, and you think of three levels for the number of calories, daily calories, and you could have all these possible combinations. So you can have 3 meals with this number of calories, 3 meals with this number of calories, so in total you can have 2 times 3, that is 6 possible combinations. So you can do a one-way ANOVA with 6 treatments. Each combination would be a treatment, and then you would realize what is the contribution of each one of these treatments, and you would consume for that 5 degrees of freedom. Okay, so now let's do the factorial design. So the factorial design would decompose this treatment effect into 3 components. So the first component is related to the number of meals, the second component is related to the number of calories, and then we have the synergies, the interactions between the two. So we have 2 levels for the number of meals, 3 levels for the number of calories, and now you know how to count numbers of degrees of freedom, and you also need 5 degrees of freedom. So these two models, they have the same number of degrees of freedom. They have the same cost in terms of samples, but they are not the same. So now with the second model, you are able to explain, okay, this part of the variability is caused by the number of meals, this part of the variability is caused by the number of calories, this part of the variability is caused by the interaction between the two. It is the same as here. So if you have different factors, it is much better to separate them in the analysis than putting them all together in just a treatment combination. And you can have factor analysis that are really complicated, and the way to calculate the effect of each one of the contributions, or each one of the contributions is different, and it is much more complicated than what we have seen of calculating the mean of the group minus the overall mean. But okay, computers know how to do that, and here you have an example of how complicated they can be. So for instance, let's say that you want to compute the effect of 2 chemicals that we will name E and O versus a control. So this is the first factor. It is what is the chemical that you are using, and you have 3 possible levels. And also the chemical O requires a surfactant, and you have 2 possible surfactants. And these chemicals will be sprayed on the animal, for instance, and then this spray, there are different sprays, and for instance the droplet size may have a difference, may make a difference, and the chemical O has surfactants, but the E and control do not have. And you have 3 different concentrations that you want to try, and then you can design your experiment in this way. So for instance, let's say you will have one animal that will be receiving a concentration 1 with a sprayer 1, surfactant 1 and chemical O, and then another animal that has a chemical O, surfactant S1, sprayer SP1, but concentration 2. So these numbers here are the number of animals. So you see that a chemical O, if you count, you have 12 animals for the chemical O, and you have also because the chemical E doesn't have surfactants, instead of 1 animal per concentration, we will use 2 animals per concentration. And we also have 12 animals for the chemical A. And the control doesn't have different concentrations, so we will use only 1 concentration for it. And we want to approximate to 12. We could have 6 and 6, but in this experiment we have decided to go for 5 and 5. So this is just to convey the idea that factorial designs, they are very flexible, so you can do whatever you want with them, and you can attribute the different components of the variability to the different factors, as we have done in this example. And by accounting for the different contributions, all these contributions, they are taken out of the error, so the residuals will have less and less sum of squares, and it will be easier to show that each one of your main factors, or your hormone, that is the treatment that you are most interested in, will have a difference, because you are comparing 218 to 34, and all the other variability you have explained with other variables. The same here with the treatment, with the meals and calories. The same here with the chemical, surfactant, sprayer, concentration. So they're really flexible, and they're so flexible that they can perform experiments with only 1 animal per combination. So for instance, let's say that you are interested in the survival of a given bacteria for the conservation of food, and then there are 3 factors that you think that can affect this survival. So one is 3 levels of sorbic acid, the other one is 6 levels of water activity, so this is how much humidity you have in there, and 3 levels of pH. So you have these 3 factors, and then what you will measure will be the logarithm of the density measured after 7 days of the treatment. So yeah, these are a lot of combinations. So you have 3 times 6 times 3, that is 54 treatments. And if you plan to do a couple of replicates per treatment, that is more than 100 experiments. Can we do it with less? And we can. We can do it with just 1 replicate, just a single replicate. Where is the trick? The trick is that, okay, so I have 54, 1 replicate per combination, that it gives me 53 degrees of freedom. I will decompose my model and count how many degrees of freedom do I need for the water activity. I had 6 levels, so I need 5 degrees of freedom. For the sorbic acid, I had 3 levels, so I need 2 degrees of freedom, 2 for the pH, 5 times 2, that is 10 for the synergy between these two, for the interactions between these two. Again, 5 times 2 for the interaction between these two, 2 times 2 for the interaction of these two, and 5 times 2 times 2 for the interactions, the third order interactions. So I need a lot for the third order interactions. But third order interactions, they are rare, so normally they don't exist. And if they exist, they are small, typically. So I can afford not to explain them. So if I don't explain them, they will go for the residuals. So if I don't explain, if I don't have to estimate these 20 parameters for the third order interactions, all these 20 degrees of freedom, they go for the residuals. And now remember this resource equation. I have 20 degrees of freedom for the residuals, and I will be able to show whether any one of these main effects or second order interactions, they are significant or not. So this is a really powerful tool. With just a single replicate, just a single animal per combination, you can identify whether your factor is important or not. And here is an even more extreme example. So let's say that you are interested in seeing how cells grow in a cell culture, in a bioreactor. And you have identified 7 variables that can make a difference. So they can affect the temperature, the humidity, pH, the concentration of oxygen, the concentration of carbon dioxide, the concentration of glucose, of amino acid. So there are 7 possible variables. For each one of them you have chosen 2 levels. So you have 2 possible temperatures, 2 possible humidity levels, 2 possible pH, and so on. So if you count how many combinations you have 128 combinations. Let's say that you are willing to perform up to 64 experiments, but you don't want to do 128 experiments. So if now that we know this trick, if I forgive the third order combinations or higher, so fourth order combinations or interactions, 5 order interactions, and so on. So if I sacrifice all of them, I give them all to the residuals, how many degrees of freedom do I need? Okay, so you have 7 variables, 7 with 2 degrees of, with 2 levels each one, and then you would need 7 degrees of freedom to estimate the main effects. And the second order interactions, there are 21. If you count how many combinations you have 21. So you need 28 samples plus whatever these 10 to 20 extra degrees of freedom for the residuals. So if I do 64 experiments, I would have still 37 degrees of freedom for the noise. So that is quite a lot. So 37 degrees of freedom for residuals, that gives you a lot of sensitivity. And even more surprising, you can even make less than 64. You can do only 32, and this is related to something that is called the resolution. So with only 32 experiments, I can have something that is of resolution 4. We don't have the time in this course to explain what resolution is, but resolution 4 means the main effects are unconfounded with two-factor interactions, and the two-factor interactions, they may be confounded with other two-factor interactions. So that is, if I'm not really interested in the second order interactions, I'm only interested in the main effects, with only 32 experiments, with only 32 combinations, not any 32, but specific ones. If with only 32, I can determine which ones of these 7 variables will make a difference in my cell growth. So this is really surprising, and we have explained it with cell growth. You can put it with whatever animal experiment you want, and you would save a lot of animals here. Okay, so what about blocking? Let's go a little bit more into blocking. So blocking, we have already introduced it, and we have presented in terms of formulas, but just to get a little bit deeper into it. Okay, so let's say that you are making an experiment and you think that the sex and age of the patient, the animal, will make a difference. And you have, for whatever reason, you have 600 males, 400 females, and you have a different number of young males and old males, and the same for females. So you would construct homogeneous groups, as homogeneous as you can in terms of the variables that you think that will make a difference. So here in this group we have only young males, and here in this group we have only old males, and it is at this level where you randomize. So you randomize this group, half of them to the new treatment and the other half to the current treatment, and the same for the other groups. So first you block, and then once you have blocked, you assign to randomly to the treatment. And yeah, this is the same, and this is just to highlight again that what we are doing is the total sum of squares we are dividing into three pieces. One of them will be explained by the blocks, the other one will be explained by the treatment, and whatever you cannot explain, it goes to the residuals. And it is a comparison between treatment and residuals that makes that will give you the whether your treatments make a difference or not. And whatever variability is explained by the blocks, it has been taken out from the residuals. So the comparison between treatment and residuals, now it is more meaningful. And here is an example of how we should block our experiments. Okay, so let's say we have calculated that we need 20 n equal 20 animals per group to distinguish to detect a difference in whatever variable we are measuring. And we have 20 females and 20 males, and we are able to process only 4 animals per day because our experiment is pretty long, so it will take 10 days to perform the experiment. So let's say that we have this design. So we have decided that on the first week, so we will use 10 days. So in the first week we will do all controls, and all controls will be female, while in the second week we will do all treatments, and all treatments will be male. So if I see a difference between control and treatment, how do I know that this difference is because of the treatment and it is not because of the sex? So these are the females, these are the males, so maybe the treatment is useless, but I see differences because of sex. And so I realized that, and then I make half of the females to have controls and the other half to have treatments, and the same for males. Okay, so and now this is my experimental design. So okay, so there well, it is a little bit better than before, but for instance here Monday I have only controls, and there is other days where I have more treatments than controls, or I have only females, so I see that it is a little bit unbalanced. So it may be that the differences that I see are because of the day. It may be that in the animal warehouse, the animal facility, there are 2 people working. The first person works on Mondays, Wednesdays and Fridays, and the second person works on Tuesdays and Thursdays. And then the differences that I see is because of this little imbalance between days, and days that see only females and days that see only controls. So maybe it is this little imbalance that and the person that is working on each one of the days. So the day should also be a block. So this is a much better design. So I'm blocking here sex, and I'm also blocking the day. So if you see, for each one of the blocks, so for instance sex, we have females and males, so we have the same number of controls in females and the same number of controls in the males. So control and treatment are balanced between males and females. And the same for the day. So within the day I have every day I have 2 females and 2 males, and I always have 2 controls and 2 treatments. And you see that every day that happens. So now every day is also balanced with respect to sex, and it is also balanced with respect to treatment. So what we have done here graphically is what we have done also here. Okay, so that would be all. So in conclusions, I would say that an important part of this would be, okay, so control what you can. This should be your mantra when designing an experiment. Control what you can. And what you can control is your treatments. You can control how you organize the data or the treatments between days and sex and age and centers and so on. That is blocking. So what you cannot control, you block it. So I think that sex may make a difference. Okay, you block it and you put the same number of control and treatments in each one of the blocks, and then you randomize the rest. So control what you can, block what you cannot, and randomize the rest. And randomize can be randomizing everything. So randomizing the position in the shelf, randomizing the order of feeding, randomizing the time of treatment, order of treatment. There are people who randomize the pipettes, they randomize the person doing the experiment, they randomize absolutely everything. And then the second message would be factorial designs are really powerful, and they can attribute the variability to the different factors, and because of the explanation of the variance by different factors, you can better highlight whether your treatment is really effective or not. And also you can reduce with factorial designs quite a lot the number of animals. And that would be it. So see you next time.